another example of being able to work with the derivatives of polar functions. So we have our g of theta is 1 minus cos theta. We're looking at the point pi halves for theta. And then we're also going through and trying to determine where the function has horizontal and vertical tangents. Now, remember, one thing that we should do automatically is say that r is equal to 1 minus cos theta. And we would find the derivative dr d theta. Derivative of 1 is 0. Derivative of negative cosine is positive sine theta. Okay. Also recall that dy dx is going to be dr d theta times the sine of theta plus r cos theta divided by dr d theta cos theta minus r sine of theta. Okay, so these are formulas that we have to have before we can find the derivative. Next thing we're going to do is we're going to go ahead and actually substitute for r, and then we're also going to substitute back in for d theta, okay, in all the spots. And so we could say that dy dx is going to be equal to sine theta plus 1 minus cos theta times cos theta. And then we're going to divide that by dr d theta, which we know is going to be our sine theta. So we get a sine theta, cos theta, and then minus 1 minus cos theta, sine theta. All right. Now, if we were to simplify this, okay, which we should, this actually works out to be a really nice simplistic sort of polar function, because the numerator, we're going to end up with sine square plus 1. So sine square theta plus 1 times cos theta, that would be plus cos theta minus cos square theta. Right? Now we're finally going to divide that by, if we were to expand this out, notice we have a sine theta cos theta and then a negative sine theta cos theta. Okay, so those would cancel out. And so that way we would just be left within our denominator a negative sine of theta. All right. And so finally, what we're going to do is we're going to substitute back in, okay? And we substitute back in at theta equals pi halves, okay? And so when we do that, we're going to end up with sine square of pi halves plus cos pi halves minus cos square pi halves divided by opposite sine pi halves, right? Now, we recall that the cosine of pi halves is 0. So these two expressions are going to be 0. We recall that the sine is going to be 1. Okay, so we end up with 1 square plus 0 over negative 1, which is just going to be negative 1. Okay, now, of course, we want to make sure that that makes sense. So probably what we should do is we should probably look at what the graph looks like. Okay, so remember our function, 1 minus cos of theta. Okay, so we're going to go over to our fruit plot, and we have 1 minus cos of theta. And we have this sort of cardioid. All right, it's called a cardioid shape because it resembles a heart. And of course, we're looking at the point pi halves. So if I was to kind of graph this, and we have like this little dimple in here, all right, to where we have something like that. So graphing this, just to make sure it makes sense, we have, and I'm going to do my best with this. I'm not that good at drawing these sorts of polar functions, so bear with me. All right, so we have this, and then we have this sort of thing. I know it's not all that good, all right, but the point that we're looking at is right here at pi halves, okay? And if we look at the actual graph at that point, the slope is more pronounced at that point than what I constructed, all right? But we do know that the tangent line at this point would be a negative, okay? So the slope here is a -1 at that point, okay? So it makes sense that we do have at least the slope at that point. Now, of course, we have to now figure out what the horizontal and the vertical tangents are for this, all right? And that's going to be a little bit tricky because we have to solve this equation, and we also have to solve this equation for 0. So let me refresh this. And So just to remind you that the dy dx was equal to cos square theta plus cos theta minus sine square of theta. And we divide that by negative sine of theta. All right. Hopefully I copied that correctly. All right. Now, first of all, we want to try to get the horizontal tangents. Okay. So for the horizontal tangents, we're going to say cos square theta plus cos theta minus sine square of theta. Right. And I think I messed that up. I think it was, excuse me, I think the derivative, and you guys can go back in the video, but I'm almost certain because we got a -1, I think it was sine square minus cos square. Okay, so that was just a memory error, but this should be it. If not, I'll just re-record it, no big deal. But this should be sine square theta plus cos theta minus cos square theta is equal to 0. Okay, now cos to the -2. Now, to solve this, what would probably be helpful is if we got everything in terms of cosine. All right, and so what we're going to do is we're going to use the fact that the sine theta is 1 minus cos square of theta. And so now I get a new equation, and I can rewrite this as 1 minus cos square theta plus cos theta minus cos square of theta equals 0, or -2 cos square theta plus cos theta plus 1 equals 0, or if I multiply through by -1, 2 cos square theta minus cos theta minus 1 equals 0. And now what we can do is we can factor this. So we can factor it into 2 cos theta plus 1 and then cos theta minus 1. Okay, so we just take a trip back down to our pre-calculus roots to be able to solve this. And now finally, we have 2 cos theta plus 1 equals 0, and then cos theta minus 1 equals 0. And so if we solve those both, we would get cos of theta equals -1/2, and then we would get cos of theta equals 1. All right, now we know that cos of theta is equal to 1 at 0 and 2 pi, all right, which are both coterminal. We know that the cosine of theta is equal to -1/2. Cosine is the x coordinate, so we're going to be in quadrants 2 and 3. And so this would be 2 pi thirds and 4 pi thirds. All right. Now, of course, we want to look at the graph to make sure that this makes any sense whatsoever. All right. And a trick that we can use is we could just change the bounds here. Okay. So for instance, what I could do is I could go from 0 to 2 pi thirds. All right. Or we're going to divide. So 2 pi over 3. All right. And remember, we're looking for horizontal tangents. Okay. So that's a point right there on the graph. All right. And if I go back through, then it looks like right here indeed is a horizontal tangent. That makes sense. Okay. And then also down here, maybe we use 4 pi thirds. So check this out, 4 pi over 3. All right. That would be right here at this point. And certainly that looks like right here, if I was to go back to the original graph of 2 pi, that certainly looks like it would be a horizontal tangent as well. Okay. Of course, the other thing you could do is just plug it back into the original function and kind of see what's going on with that coordinate. Okay. Now over here at 0, because remember we got these other points too, 0 and 2 pi. All right. They might be extraneous. Okay. Because we know at 0, okay, and 2 pi, this is more of like a vertical tangent, if you would. Okay. So we should check this. And these are definites, okay, from the graph, but these are questionable. Okay. So when we do this, we're looking at this point, and it doesn't look like in the graph that that's going to be a horizontal tangent there. Okay. So we might be wary of that, and we might say that that's not going to be the case, okay, from the graph. Okay. Now, we also have to find the vertical tangents, which is significantly easier because all we have to do is just set negative sine of theta equals 0. And that means that we have sine of theta equals 0, and this is for our vertical tangents. And that happens at 0, pi, and 2 pi. And again, we're going to go back to the graph, and we're going to kind of cheat a little bit, and we can just say, okay, well, I know what's happening at 0, okay, and I know what's happening at 2 pi. So those don't look like that they would be vertical tangents, okay, because of the dimple there, okay? But if I just looked at pi is right here, okay? And it looks like the slope is going to indeed be vertical at that point, okay? So if we go back to the graph of this thing, and I think I erased it, okay? What we're really looking for, I'm going to try to draw this again, okay? Sorry if I offend anybody. All right, so that's 1, and I know it's not that good, sorry. But remember right here, okay, this is a vertical tangent when theta is equal to pi. And then right here, this is a horizontal tangent. Remember, we had 2 pi thirds. And then over here, we had another horizontal tangent, and that was at 4 pi thirds. Okay, so that way we can go through and we can kind of see what these horizontal and vertical tangents look like. But right here, this isn't necessarily a tangent at all. Okay, so because we can't necessarily touch the function without touching any other point. Okay, so if we did that, that doesn't make a lot of sense to us. Okay, so we always want to verify from the graph what our actual solutions are going to be. Okay, just because sometimes when we solve trigonometric equations, they give us more angles that are necessarily in the domain. Okay, so that's dealing with derivatives of polar functions. Not too bad. Okay, so in our next videos, we're going to start taking a look at areas of polar functions. And then finally, we're going to conclude with arc lengths of polar functions.